Hello everyone, my name is Junali and I'm a PhD student at Virginia Tech. Today I would like to talk about near-field tsunami forecasting based on a tsunami run-up response function. Let me briefly explain how the presentation will proceed. The first part will consist of a brief introduction, and the second part will be about a new model called a tsunami run-up response function, or TRF model that can be used to forecast tsunamis. In the third part, the performance of the TRF model will be discussed based on 100 random cases and the 2014 Chile tsunami case. Then I will conclude my presentation with some final remarks. Introduction. A tsunami forecasting system, especially for a near-field tsunami, is needed because tsunamis can arrive within a few minutes to coastal communities and cause massive damage to life and property. The map on the left shows the study area of this presentation, the northern Chile region. There was a moment magnitude 8.2 earthquake in 2014, and as shown in the figure on the right, the first tsunami wave arrived at the equictide gauge within 20 minutes. This example shows how fast and accurate the tsunami forecasting system should be. Since a tsunami run-up is directly related to tsunami damage, a tsunami forecasting system should have the capacity to predict the tsunami run-up distribution along the coastline to mitigate damage and build resilient coastal communities. Usually, a tsunami model is used to predict the tsunami run-up distribution from the earthquake information. There are three characteristics that the tsunami forecasting system should satisfy. First, it should be fast because delayed forecasts can reduce time for evacuation. Second, it should be accurate because false alarms can cause confusion and can exacerbate the damage. Third, it should be stable because tsunami forecasts must be possible under any earthquake condition. However, none of the tsunami models satisfy these three characteristics at the same time. For example, the physics-based numerical model is currently the most accurate method for predicting the tsunami run-up distribution. However, the problem is that it is computationally expensive and there could be a stability issue depending on the numerical scheme and other conditions. For this reason, a pre-computed database is widely used for tsunami forecasting, which could provide fast and stable prediction by selecting the best matched simulation result. However, the problem of the pre-computed database is that it can have the substantial error in real-world scenarios that do not exist in the database. An analytical model is also fast and stable, but it is not accurate compared to the numerical model because the analytical solution is derived from the ideal conditions like flat bathymetry or uniform slope conditions. To overcome the limitation of tsunami models, we developed a new model called Tsunami Run-up Response Function TRF model that can be used to forecast near-field tsunamis rapidly, accurately, and stably. TRF model. The basic concept of the TRF model is to decompose the tsunami run-up distribution Rx into source run-up Sx and topography run-up Tx, where the x is defined as a line parallel to the coastline. The source run-up Sx, the red line in the right figure, is the leading order contribution that can be represented by the Okawa and Sonolaki's 2004 formula. From now on, I will call this formula an OS formula. The topography run-up Tx, the blue line in the right figure, is the residual part remaining after subtracting Sx from Rx. We define a topography run-up divided by a source run-up as a normalized topography run-up. This normalized run-up is independent of the tsunami source and is associated with local topographic characteristics. Based on this concept, the TRF model can predict the tsunami run-up distribution by modeling the source run-up from the fault parameters and by using the normalized topography run-up. In this presentation, I will summarize the key points of the TRF model. Please find this recently published paper if you are interested in the details of the TRF model. This figure shows the procedure of building a TRF model. The first step is to simulate 729 scenarios using a physics-based numerical model and extract the run-up. The second step is to apply the OS formula to obtain the normalized topography run-up, or NTX. And the last step is to fit the fault parameters and the OS formula coefficients to the second-order polynomial model to obtain the response surface methodology, or RSM functions. To be specific, we designed the 729 scenarios like the left table, considering the historical earthquake activities in northern Chile. We used a Bushnell type model called Basilisk, which employs both adaptive mesh refinement and parallelization techniques. This figure shows the result of step 2. If we apply the OS formula to each simulation result, we can obtain the normalized topography run-up. The gray part represents the range between 5th to 95th percentile of 729 simulations, and the black line represents the median value of the normalized topography run-up, which will be used for prediction. This figure shows the result of step 3, which is the comparison of the OS formula coefficients A and B between the target value and the prediction. The target value is the coefficient obtained by fitting the Tsunami Run-up distribution to the OS formula, while the prediction is the coefficient obtained by the RSM functions. Once the RSM functions and the normalized topography run-up are derived, the TRF model is ready to predict the tsunami run-up distribution. From now on, I will explain the procedure of predicting a tsunami run-up distribution. The first step is to convert the fault into a series of hypothetical faults using an angle projection, or AP method. The second step is to estimate the source run-up based on the OS formula. And the last step is to estimate the tsunami run-up distribution by combining the source run-up and the normalized topography run-up. The OS formula is only applicable to the fault where the strike direction is parallel to the coastline and the slip direction is perpendicular to the coastline. However, since it is not the only case that occurs in nature, we developed the AP method that can convert the fault located in any direction into a series of hypothetical faults applicable to the OS formula. The AP method starts with adjusting the strike angle and rake angle. For northern Chile region, we assume that the coastline is parallel to north-south direction. In this condition, the adjusted strike angle, theta, and the adjusted rake angle, lambda, are defined as the right equations, where the alpha, beta, and gamma are the coefficients that should be calibrated in advance. Then the adjusted fault is rotated until the strike direction is parallel to the coastline or the x-axis, based on the assumption that the near-field tsunami propagates in straight direction. Then the AP method defines a series of hypothetical faults having the slip direction perpendicular to the coastline. For each hypothetical fault, the source run-up can be obtained based on the OS formula, where the coefficients A and B could be obtained by the RSM functions, and the coefficient C could be obtained by the epicenter latitude information. And the final source run-up is defined as the red line, where the maximum values are extracted along the coastline. Finally, the tsunami run-up distribution can be estimated by combining the source run-up and the normalized topography run-up. Results. To validate the TRF model, we simulated extra 100 random scenarios that were never used to build the TRF model. This figure shows one example among 100 scenarios where the black line with circles represents the numerical simulation result, while the red line represents the TRF model result. The mean normalized root mean square error, or mean NRMSE, of 100 random cases was about 7.7%. And the computational time of the TRF model was about 0.01 second per scenario. And the TRF model was always stable since it solves a simple algebraic equation. We also applied the TRF model to the 2014 Chile tsunami case. The earthquake fault parameters were chosen based on the USGS focal mechanism and Blazer et al. 2010's scaling law. When we compared the RMSE between the model prediction and the measured data, the error of the TRF model was similar to that of the numerical model. On the other hand, when we compare the computational time, the TRF model was much faster than the numerical model. Conclusions. In this presentation, we introduced a new model called the Tsunami Run-up Response Function, TRF model, that can be used to forecast near-field tsunamis for any combination of fault parameters in real bathymetric conditions. The results show that the TRF model can estimate the tsunami run-up distribution rapidly, accurately, and stably. Although the TRF model is currently applicable only to a near-field tsunami, uniform slip distribution, and a tsunami generated by an earthquake, we believe that the TRF model has the potential to significantly reduce loss of life in coastal communities by supporting rapid, accurate, and stable tsunami forecasting. This is the end of my presentation, and thank you very much for your attention.